that's right. Section 8, is that correct? Yeah, let's do that. So the rest of statistics, so everything else in the entire statistics world, right here in this slide. No, I'm just kidding. Good stuff. So if you'd watched the videos, you're familiar with what we call T-test. Someone heard of a T-test before? It's not what I do, like Earl Grey and Jasmine. It's not like that. T-tests are ways that we can compare differences between groups, okay? If you go back and review that, you'll see that it's a very common statistical method we're going to try to determine. So for instance, if I were to have 3 sets of patients and I were to give this group hydrochlorothiazide, give this group lisinopril, and then I give this group lisinopril hydrochlorothiazide, if I was trying to compare the differences, we're going to see that a T-test isn't really good for that. T-tests are good for 2 groups. I could do lisinopril and ACTZ. We're going to look at what we can do when we have more than 2 groups here. And that's where we're going to talk about ANOVAs, ANOVAs. When you see that's what we're talking about there. So getting into it, that's kind of anyway, so ANOVA stands for analysis of variance. This is where we're going to be able to compare more than 2 groups with one another to determine if there's a statistically significant difference between them. Okay, if you're just doing 2 groups, comparing, say, blood pressure reduction after initiating a new medication, that can be done with 2 groups with a T-test. This is going to be kind of a more complicated. We're going to include more than 2 groups here. Okay, so again, it's called analysis of variance. You just hear ANOVA. That's what we're going to refer to it as here. And kind of what it does is it will kind of help us to determine, is there a difference anywhere between the 3 groups? It won't say that group 1 is different than group 2 versus group 1's group different than group 3. We have different tests for that. It's just kind of telling us, if I compare 3 groups together, is there a difference at all between them? Okay, because again, if there's not, and again, the null hypothesis would be what? There's no differences between the 3 groups. If it's the ANOVA is negative there, right? If it's not significant, then I can say, okay, well, my job is done. I don't have to look any further. However, if I do find a significant difference, then I can start to dig further. And that's where we're going to talk about some of these tests that kind of go further from there. But basically, you can think about it like a T-test being done with more than 2 groups. I can do it with 4 groups, 5 groups, 6 groups. It really doesn't matter as long as it's more than 2. Okay. And again, if I were to ask on a test, say for instance, I can ask a question where I'm like, hey, you have 3 groups you want to compare X, Y, and Z to. What type of statistical test would be appropriate for this? Okay. And if I had a T-test, you say, no, that's not appropriate because you have more than 2 groups. If I just had 2 groups, T-test is fine there. Anyway, now what I could do potentially is I could say, well, if I had 3 groups, I can compare 1 to 2, and I can compare 1 to 3, and I can compare 2 to 3. What happens when I keep making more and more comparisons? Because again, my significance level is set at 0.05. The more times you do a test, you run a test, and we'll run a comparison, the more likely you are to find something that is significant, right? Does that mean it was actually significant? No, because when I find something that's significant, less than 0.05, that still just means that, 0.05 just means there's a 5% chance this is just due to random chance alone, right? So again, by running the same test over and over again, we call that a multiple comparisons test, you're more likely to find a type 1 error. And a type 1 error means you're finding a false positive. You're finding a difference and you're rejecting the null hypothesis when there actually is no difference in that group. Okay, type 1 errors are not good. You don't want to perform those. So we're going to find ways to get around that by using things like ANOVA are going to help us when we have multiple groups here. Okay. So anyway, again, 2 or 3 more means totally great when using ANOVA. So a couple different types of ANOVAs you can have here. One's called the Oneway ANOVA. This is where we're going to compare the means of 3 or more groups. And again, the assumption is these are all going to be following a Gaussian distribution, a Gaussian population here, right? We'll talk about non-Gaussian tests a little bit later on. And again, what's another name for like a Gaussian distribution when I'm doing like a test with those? You guys heard the term parametric? Talking about parametric tests, this is what we're referring to when we're working off the assumption that we have a Gaussian distribution. It's called a parametric test. So an ANOVA is an example of a parametric test. Okay, that's important. We're looking at non-parametric tests later on that are going to be considered to be non-Gaussian. They don't fall into that assumption there. Okay. So again, looking at this example, here's one from '93 that was looking at the LH levels, luteinizing hormone levels, the changes you found in women runners, right? So again, looking again just at females, we're looking at those who are going to be considered non-runners, those are considered recreational runners, and then elite runners. And again, who sets the definition for what elite runners versus recreational? The researcher, right? So they could say, hey, you run this many days a week, or you run this many miles in a month, whatever happens to be, they set the definitions there, right? And again, your job as the providers to look at that and be like, oh, does that actually make sense? If you were, say, focusing on sports medicine, and you're like, okay, well, they use a definition that I really don't feel like is characteristic of elite runners. Maybe that can skew your what you think about that data or what your interpretation is going to be. But let's just say we're going to break them up into these 3 groups here, okay? We're looking at the distribution of the hormone levels. Again, these are going to be considered to be at log normal, so don't get hung up on that. Just know the LH LH levels can vary quite widely in these females, and so we're using the log normal of that to try to make it a little bit easier to analyze here. Now again, when you're looking at these studies, they publish every single data point that they took. No, oftentimes you're just getting the summary data. You're just getting the graphs, and again, you can make interpretations based off of that. Now, can you just safely assume that, yes, all that data is correct? You should take it with a grain of salt, but remember, if you're looking at a reputable journal, it is considered to be peer-reviewed. What does that mean? That means someone else in that field who's considered an expert, hopefully, has looked at that and reviewed it and says, yes, this makes sense, okay? So that's why we prefer to use peer-reviewed journals, because that way, I mean, there's journals out there, I can publish anything. If you pay a big enough fee, I can get anything published. Doesn't mean it's in a reputable journal, doesn't mean it's going to be reputable data, okay? So again, peer-reviewed journals is why we like that, because someone else has at least looked at this and usually an expert in the field and can check off on it. So anyway, they're looking at the distribution of the hormones. Again, we'll look at the graphs here in just a second. And basically what they were determining was, can we look at the LH levels, and are these significantly different depending on the runner status of these women here, okay? And we'll show you the graph here. Now again, we'll show you the mean of the non-runners based on the standard error of the mean. We'll see if this is distinct or not from the other runners here in just a moment. So looking at this, we can find here's the mean values plus their standard deviation. Now what affects the standard deviation? Just the variability. That just is quantifying how much of a spread of the data we're actually having there. So again, I'm not going to put every single data point on here, but this graph is good because it can kind of tell me the spread of the variability here. And again, looking at your ends helps us because it helps us to say, okay, well, how many people are we actually including in all these groups here? So we had about 88, 89 in the non-runners and recreational, and only about 28 in the elite runners. Does that make sense? Because again, you'd have less elite people that probably fit into that elite category. So again, your sample size is going to be smaller than that. But again, what do you think that would do to your variability in the data? You're probably going to see more variability because again, you are more likely to find those outliers when you only have a small sample set, right? So anyway, looking at that, you can see what the log of the concentration here is the mean values. Here's a graph in a couple different ways with the standard deviation and then the standard error of the mean here. And notice, remember we said standard error of the mean takes into account the sample size that you're looking at. So what do you notice about the standard error of the mean between these three? Well, one, they look like little TIE fighters. The other thing is that the non-runners had the biggest group here. The non-runners and the recreational runners had the larger group, so they have much shorter standard error of the mean bars because, again, that is directly affecting that. If you go back to our first lecture, first or second, you'll see that's in the denominator there. But the elite runners had a smaller group, so they have a lot wider variability there, so the standard error of the mean bar is a little bit wider there. Okay, just something to note, okay? And so just based off of this, what can you tell about the differences? Like, well, it looks like LH levels tend to be lower and the elite runners and the recreational runners, but can you say there's any statistically significant differences between these two? Not yet, right? You can't just look at this based off the error bars and make any determinations. But let's look at it and see if we can determine any differences with the actual data here. Now, what I could do is I could do several t-tests. So I can compare elite versus recreational, elite versus non-runners, and then I can do recreational versus non-runners. I could do that, but again, every single time I do that, I'm more and more likely to make a type 1 error. Okay, that means I am going to be just running the same comparison over and over again until I find something that fits. That's called data torture. We don't want to do that. So what we're going to do instead is just to run an ANOVA that will compare all of them together to see, is there any difference anywhere? And then once we find that, if we say, yes, there is a difference there, then we can start to dig down. And we'll look at some different tests we can do that will help us to make sure we're not going to make those type 1 errors. We're going to make sure we don't have a false positive that shows up here. Oops. Anyway, so looking at that, we ran a one-way ANOVA. So we're comparing all three groups all at the same time. And we found that the one-way ANOVA p-value is 0.0039. Okay. The question is, what does that mean? Well, in this case, the null hypothesis would be what? That the runner status has no effect on the LH level. They should be all pretty much identical, just based off of random. Any variability we do find is just random chance, right? So if I'd done this study with a different set of women, I'd probably find the same exact results or something that would be, again, not significant. Okay, just random chance. If I were to do, in this case here, I have a p-value that is 0.0039. So again, that is less than 0.05. So would you consider this statistically significant? So yes, there is a 0.39% chance that I would have found results like this or more extreme than this just due to random chance alone. So it's very unlikely that this is just due to chance. There is a difference between one or more of these groups. I just don't know where it is yet, but I know there's a difference somewhere. Okay. So again, as I mentioned, the null hypothesis, I can reject this now because my p-value is less than 0.05. I know that yes, there's a difference somewhere in this group. And again, I don't know where it's at yet, but I'm going to find that out in just a few minutes here. So again, your assumptions here should be the same based on the unpaired t-test. Now when I say unpaired, what do you think that means? Unpaired means I have independent samples, right? So I'm not using the same person more than once. I'm not using twins or anything like that where you'd have influence on those values there. So if you see a paired t-test, that's where I'm using, say, the same person twice, say pre and post. I'm using twins, I'm using whatever. But an unpaired t-test is the most common one you run into. And so the same assumption should be made when you're using a one-way ANOVA. And again, the sample should be randomly selected. That helps us to make sure we have a Gaussian distribution. The observation should all be made independently, so I'm not measuring the same person twice. Or I measure someone as an elite runner, and then I saw them 6 months later, and they had an injury, now they're a non-runner. I wouldn't want to measure that person, right? I want to make sure that they only get measured once in that study there. And then again, you have to, you're assuming you're pulling it from a Gaussian distribution. And again, hopefully the standard deviation of all populations are identical. They're going to be close, but again, that's a test we can run for that. So don't get so hung up on specifically how it's working here, but just know that we're doing some complicated math on the back end of this to try to determine, okay, where there's a difference here between these three groups. Again, we don't know where it's at yet, but we're going to find that when we can do some alternative testing here in a minute. But again, the null hypothesis is that there's no difference between any of the groups. If it's less than 0.05, you reject that and say, yes, there's a difference somewhere. Now you got to find it. Okay. Now you can do a repeated measures ANOVA. This is actually going to be the same same difference between unpaired and a paired t-test. So again, if I were looking at someone LH levels of someone when they were considered a non-recreational runner and then a non-runner, and then say I put them on a training regimen where they became an elite runner and measure LH levels afterwards, that was where you can use a repeated measures ANOVA. I'm measuring the same person twice, different settings, because that person will have an interplay there on their own values. That's where that's going to be able to be used there. Again, not used as commonly. One-way ANOVAs are going to be the most common ones you run into, most likely. But again, going to be used on the same person twice, on a set of twins, on the same sample, maybe run in parallel, anything like that. You can have a two-way ANOVA. Two-way just means that you're going to be using basically additional factors. You're going to be using additional variables in this. So you have the same dependent variable, but you're going to have more independent variables adding in. So in this case here, we can look at LH levels based off their running status, but now let's also include age, right? Age levels probably have a role to play in LH level, or age has a role to play in LH levels, as you know. So we can use two-way ANOVA to help us with that as well. So basically, with a two-way ANOVA, we can test basically three null hypotheses and actually get three different p-values. So again, it gets more complicated. These are not done as commonly, but again, just trying to at least get you some familiarity with it. The first thing it's going to do, and again, we're going to use this example of the runners, the three different categories of runners, and we're going to use age as well to see what effects it has on LH. So first off, we can look at the interaction between age and the runner status here. So we can look to see that the null hypothesis would be that there's no interaction between the two factors here. So basically we take all the elite runners, look at the effect of age, and then on the outcome of LH. You take all the recreational, do the same thing, and then all the non-runners do the same thing. You're looking at the interaction between age and the running status as what the outcome is going to be as far as LH goes. That's one p-value you get from that. You get another p-value that's just looking at the first factor. So basically you're looking for, in this case, we'd be looking at the running status of the patient based off the LH concentration. And then the second factor would be looking at just age. So again, you get three different p-values. You can kind of determine already, okay, well, is it the interaction of the two variables together causing a difference, or is it just going to be one or the other? Okay. And again, the math is such that you don't have to worry about the type 1 errors when you're doing this sort of thing there. You have to kind of take into that into account already. Okay, so let's figure out, let's say we want to do some tests afterwards. So I get a positive test. I can find a significant value on my p-values when I do an ANOVA, a one-way ANOVA on these runners. How do I figure out which group it is specifically that is going to be the difference here, where the difference between which groups are actually significant? This is where we're going to have multiple comparison tests. Now, what did I just tell you about multiple comparisons? Yeah, they're not good, right? They're going to increase your chances of finding a false positive if you're using 0.05 for your level of significance for each single one. What we actually have are going to be some different tests that we can run that kind of modify to make it more difficult to find significance, but make it more likely that you're not going to find a false positive. Make it harder to get a type 1 error. And so sometimes you'll have what we call family-wise error rates, where in some cases you may even take that 0.05 and divvy it up amongst all the different comparisons you're going to make. So I may use 0.05 divided by 3, and that means that each one of those comparisons I make has to meet that level of significance in order to be considered statistically significant. Okay, that's one way to do it. There's some other tests as well we can do to try to just kind of dig deeper differences are. So again, looking at this, we said we had a very small p-value for our ANOVA, the one-way ANOVA for that previous example. We want to find out which group are statistically significant between the others, right? Now again, there could just be one difference between the groups. There could be more than one that's statistically significant. We're going to find that out in just a second here. So as I mentioned, when you're looking at the family of comparisons here, the significance level kind of gets redefined. So that way it's harder to achieve significance with each of those individual comparisons, but that also means that if you're less likely to make a type 1 error, that conversely means you're more likely to make a type 2 error, right? Because again, they kind of go hand in hand. So the less likely I am to make a false positive, the more likely I am to make a false negative. So I can't find a difference. That usually means I don't have enough power. I need to have more patience in order to actually get a difference here. So again, one comparison, if I was just looking at, say, runners to non-runners, or recreational versus non-runners, I could just compare those two directly, use a t-test, and I have no problem there. I can use 0.05 as my normal level of significance. If I'm using a family of comparisons, I kind of have to divvy that up, right, to make sure that I don't make one of those type 1 errors. So, and that means that the more comparisons I make it easier or more difficult to find significance. More difficult, because again, that 0.05 has to get divvied up more and more and more and more. So the more comparisons you make, the harder it's going to be to find the significance, right? So that means when you're going into an experiment, you have to make sure you have a good idea of what comparisons you want to make already. You can't just go and like, let me try this comparison, let me try this comparison, let me try this comparison. Because again, you're going to find it so difficult to achieve significance that the chances of making a type 2 error are astronomical. They're going to be very, very high. That's actually going to be occurring there. I shouldn't say astronomical. It's very, very likely you are to make a type 2 error. So I mentioned one of the tests we'll use here is one called the Tukey Test. I'm sure there's a Dr. Tukey somewhere that came up with this, but basically what they end up doing is they will kind of readjust the confidence intervals in order to make sure that the statistical significance you're finding is not going to be considered a type 1 error. So this is the most common one you run into, and when you're doing multiple comparison tests after a one-way ANOVA, if you look at the lectures online, there's one called the Bonferroni's equation. We also use Bonferroni pretty commonly. But again, this is the one we use with ANOVA most likely. So looking at this, we can actually do the comparison between the different groups here, right? So again, our level of significance, because again, we're looking at differences between the different groups, so 0 would be considered significant here. So this means, and again, here are my confidence intervals, and notice I'm doing each comparison here. So recreational versus elite, non-runners versus elite, and then non-runners versus recreational, right? So basically, what you can see here is that if the line crosses 0, if the confidence interval crosses 0, because I'm looking at differences, I'm doing one subtracted from the other. If the difference crosses 0, because if the values are the same, the difference should be 10 minus 10 is 0, right? So again, if I'm looking at the difference between the two groups, if it crosses 0, that means it's non-significant. That means I cannot say that there's a statistically significant difference between these groups here. So based off of this, what can you say? Which one was actually statistically significant? The non-runners versus the recreational, which kind of makes sense, right? The difference between, say someone who sits on the couch all day long versus someone who gets up and runs a mile every day is probably a lot different than someone who, say, runs 1 mile a day versus someone who does, say, 5, whatever the case may be. And again, the definitions are determined by the researchers there. Anyway, so based off of this, and again, when you do things like the Tukey test, basically what they're doing is they readjust the confidence intervals and make them wider. So that way you're more likely to cross that 0 line and more likely to say that this is non-significant, right? So it just makes it more difficult. That mean has to be further away from the 0 in order to make sure that it actually is truly statistically significant, okay? And again, what's the other way I could try to get these confidence intervals more narrow? More people, right? So again, if I was looking at 300 runners instead of 30, that would definitely narrow up my confidence interval pretty significantly there, okay? Because again, I'm taking out less variability. I'm saying, hey, this is probably a lot closer to what the actual population values are. Okay, and again, looking at this, this kind of shows you the same thing, just in a different representation here. So again, looking at non-runners versus recreational, this is the difference in the mean. So I'm subtracting one mean from another, and you can see this difference here with the confidence interval. If it does not cross 0, it is considered statistically significant. And you're looking at this, you find that there's only one group that is going to be statistically significant. Notice here, it goes from 0.027 to positive 0.27. that crosses 0, it's non-significant. This one goes from negative 0.17 to 0.13, crosses 0, it's non-significant. This is the only one that retains significance here, okay? But again, notice why I had to do that first. I couldn't just have done t-test between each of the groups there, because again, you run the risk of running into that multiple comparisons fallacy. Yes, sir.
Kind of silly question. Both values have to be positive to be statistically significant.
They could be positive or they could have been negative, right? So depending on which one you subtract from which would have dictated that, right? So for instance, the LH levels were lower in the recreational runners and subtracted that from the non-runners, it would be positive. If I did the other way around, it'd be negative. It doesn't really matter as long as it doesn't cross that level, that threshold, that 0 threshold there. Okay, so again, note here, this is when we're looking at differences. I'm subtracting one from another. 0 is my threshold. If I really look at the ratios, so I was dividing one versus another, you're going to find that the threshold here is going to be 1, right? Because again, 10 divided by 10 is 1, right? So again, that's if there's no difference between the groups, then it would be 1 in that case there. So looking at this, again, non-runners versus recreational, is found the ratio is 1.38. So the confidence interval went from 1.09 to 1.74. That tells me that because I did not cross 1, that this would be statistically significant. These two, notice they still cross 1 in this case here, so both of these remain non-significant. It doesn't matter if you do a difference between the means or if you do a ratio between the means. You just have to make sure you're looking at the right threshold for what was considered to be significant. Okay, that makes sense? So again, a lot of the questions on the test may come up as something like, hey, here are the values, here are the results from a study. What's your interpretation of this? And you have to look at the confidence intervals and to determine, is this statistically significant or not, right? That's part of the interpretation aspect of this. I don't care that you can calculate a CI. I can't do it, but I can look at a CI and tell you, okay, what does this mean? Does this mean there's actual difference here or not? Okay. Now again, the range of the CI is also really important here as well, because again, that's what I'm saying is like, this is my 95% chance I think this is the actual population mean is somewhere here, right? This actual difference is somewhere within this group here. The wider that is, the less, less I can say like, well, if it's pretty close to 1, maybe it's not so clinically significant, versus if it's very narrow, it's very tight and compact, the confidence interval, I can be really, really well assured that, okay, that range is very narrow. I can be very well assured that the actual true mean is definitely somewhere in there, right? Even just more confidence in that smaller range. Okay, so again, looking at this for the 95% confidence interval between differences, if it includes 0, it's non-significant. If you're doing a ratio and it includes 1, it is non-significant. Okay, so make sure you keep those ideas in mind. Anytime you're doing a ratio, 1 is your level for significance. Anytime you're doing a difference in means, 0 is going to be your level of non-significance, your threshold there. Okay. All right. Now again, that 5%, we just basically divvied it up and applied it to each one of those tests there, so it made it more difficult for something to be statistically significant, but that also made sure that we were not going to be making a type 1 error. So that way, when we actually say that we found a difference between the non-runners and the recreational runners, we're pretty confident that's actually true, and we're not just defining something by random chance alone. Okay, that's kind of the benefit from doing those additional tests there. It gives us more confidence that we can say that, yes, this is an actually true thing there, right? And confidence in the thing that I can say, okay, yes, I can apply this to actual patients. Hey, I think your LH level should be different if you're a runner versus a non-runner. Okay. Again, based on where you set your level of significance, your alpha, you could say 0.05, you could say 0.01, and depending on that, whatever you want to set it as a researcher, you may find that they may remain statistically significant, they may not. Most people do 0.05, so you can just kind of reference back to that. That'll be our big standard here. But just note, you may see some studies will do 0.01. That's just something that we want to be a little bit more stringent on that. Okay. So again, looking at these multiple comparisons here with more groups, the confidence intervals are going to become wider. So if I was looking at, say, non-runners, or say I was looking at non-runners, elite runners, cyclists, and swimmers, looking at LH concentration, the more groups I include with that, the more comparisons you have to make. And so the more comparisons you make, the more likely you are to make a type 1 error, which means that you need to be more conservative. So that 0.05 has to get divvied up amongst all of those comparisons, which makes it more and more difficult to actually find a difference. Okay, so again, chances of a type 1 error go down, but your chances of type 2 error are going to go up the more comparisons you have to make here. Okay. All right. So again, even if you only have 2 groups, you could use a one-way ANOVA, but most of the time, if you just have 2 groups, unpaired t-test is going to be fine when you're actually doing that. But just to show you the number of groups that you have, and then the number of pairwise comparisons you'd have to make, right? So again, if in that running example, when we only had 3 groups, we just had 3 comparisons. But notice here, if I were to have 10 groups, I'm making 45 different comparisons. 0.05 divided by 45, it's a pretty small number, right? So that means you're going to have so many more comparisons to make here. It's going to be very, very difficult, assuming you're doing statistically rigorous methods, to actually find significance there. Type 2 error is going to be very, very likely to occur because you just don't have the power to really show the differences there anymore. Okay. All right. Now, again, we can have, and I'm trying not to go over too long, but again, looking at multiple comparisons, these are going to account for things like intertwined comparisons as well. And so just know that looking at the pairs of the means here, looking at the differences here, even though you may not get an exact p-value, just by looking at the actual confidence interval, this is going to be enough to actually tell you if there's a statistically significant difference there or not. Okay, so that was an example of a parametric test. The ANOVA is a parametric test. The Ttest is a parametric test. What happens if you have to use something like a non-parametric test, say a non-Gaussian distributed? We're going to be running into a few different types of things we can do here, right? Again, when you have a non-parametric test, that means you make no assumptions about the population, right? There could definitely be outliers. That's fine. We're going to take that into account. Typically, you find with non-parametric tests, it is more difficult to find significance because you're not making that really big assumption that your data is normally distributed, okay? And oftentimes, if you're not really sure if you have a normally distributed data set or not, you just go ahead and say, well, I'm going to default back to using non-parametric data. And oftentimes the difference here, because remember when we talked about means and medians, which ones are more affected by outliers? Means were definitely affected by outliers, right? Medians were not, because medians just what? Just that middle value, right? If you rank everything according from highest to lowest, you'd find the median is just that middle value there. Outliers don't really affect the median quite so much. So you can think of when you're switching from a parametric data set, using Gaussian distributed data, that you can use parametric tests and you can use means because, again, you're assuming there's not going to be these outliers there. The outliers are what kind of distributes the data such that it's not normally distributed anymore. If you don't say that assumption there, you can switch over and use the non-parametric data. And instead of using means, you're not using medians. You're using ranks of data in order to make these comparisons again, right? It's a little bit harder to make significance, but you're less likely to make it one of those type 1 errors because, again, we're trying to make sure that we include those outliers, but they're not really going to affect our results all that much. Okay, so again, non-parametric tests make no assumptions about the distribution here, and they're going to be ignoring the values themselves, but just using the ranks of those values. And again, the computer systems are doing all of this. We're not actually having to do this ourselves, but I just want to show you that when you see someone talking about a non-parametric test, this is what they're referring to, basically. One of the big ones we use here are going to be when we're comparing 2 unpaired groups. We're going to have what we call the Mann-Whitney test. You may see like a Mann-Whitney U-test occasionally. Basically, this is a non-parametric test to compare 2 unpaired groups and compute a p-value. This is the non-parametric version of a t-test. Okay, good to distinguish because, again, it may ask you based off of, on a test question, it may ask you, hey, this is the kind of study you want to do. What test would you want to use for that, right? And I'll tell you it's normally distributed, it's not normally distributed. You need to figure out, hey, do I want to use a Mann-Whitney test? Do I want to use a t-test? That can be useful here because, again, a lot of the interpretation of the medical literature is like, did they even use the right test to show what they're actually trying to show? And a lot of times they are, but you don't want to take it for granted, right? You want to be able to be a little bit more critical about it. Anyway, I'm not going to belabor all the points on how that actually works, but just know they're going to be ranking the data instead of looking at the actual values, and then they'll make a comparison to see if there's a true difference between the groups. And right, so when you're looking at the p-value, again, you can see that we're comparing these groups together. Again, we're not making any assumptions about the distribution. But basically, we're going to get a p-value, and again, anything less than 0.05 is still considered statistically significant. So that actually has not changed at all. Just know that if you have non-parametric data and you want to compare 2 unpaired groups, a Mann-Whitney test is going to be good. Okay. Now, something else you could do if you have, say, 2 paired groups. So if I was saying you're doing a pre-post in the same individuals, if I was using twins or anything like that, you're going to find that we're going to use what we call a Wilcoxon matched pairs sign rank test. And again, I do not name these things, unfortunately, but they get more complicated as you go, unfortunately. But this is basically using like a paired t-test. So you can use this as an alternative to a paired t-test if you have non-parametric data. Again, I'm not going to give you the actual steps here, but just, again, the same assumptions go into it. The only difference is you're not assuming the data is normally distributed. Okay, but still trying to compare the same things, paired data together, and you still get the same sort of p-value, same level of significance is important here, 0.05. Anything less than that is significant. Yes, sir?
What was the difference between the Mann-Whitney and the Wilcoxon?
So the Mann-Whitney and the Wilcoxon max, Mann-Whitney is unpaired. The Wilcoxon match pair sign rank test is paired. Pairs right in the name, so that kind of gives you a clue right there. Okay, The Mann-Whitney test is going to be for unpaired, non-parametric data. You go back and review here. We'll kind of show you that. Looking at this Gaussian population versus non-Gaussian, you can see here Gaussian. You can use the problems with using things like non-parametric tests. Typically, they tend to be too conservative, and you tend to be more likely to make a type 2 error. Versus if you make a non-Gaussian population and you use a parametric test, you tend to be more likely to find a type 1 error, and you find a false positive, as the case may be. So again, this is some of the issues you run into by using these different types of tests. Okay, so let's go ahead and cut it there. Any questions I can answer for you? Again, I will probably, I'm trying to think, the next session is in person, is that correct? Yeah, so we'll finish this up and we'll kind of keep moving on with that, and then we'll go from there. All right, well, thanks, and I guess I will not see you guys tomorrow unless you want to stop by and just hang out. It'll be, I'll put out a message and I'll make sure that is clarified for you guys. Yeah.